Hello guys, and welcome to another calculus video. We have an absolutely amazing video today. I think you guys are really going to enjoy it because in this video we are going to be integrating ln t dt from 0 to x 7 different ways. So I'm going to show you 7 different ways to do it, starting from the most simple, integration by parts, the classic way of doing it, and we're going to move through definitions, through power series, and working up our way all the way to iterated integrals. So if you want to see the much more bizarre methods of integrating, definitely stick around till the end or skip to the end if you want. And yeah, let's go ahead and jump into the methods. Let's go ahead and start with method 1. Method 1 is going to be just integration by parts. So we're integrating from 0 to x ln t dt. So using integration by parts, we're going to get t ln t evaluated at x and at 0. And we're going to be subtracting the integral from 0 to x of the derivative of ln t is just 1 over t, so of 1 dt. Now, this is just going to be x ln x minus the limit as t goes to 0 of t ln t minus x. So overall, we're going to have x ln x minus this limit as t goes to 0. And we're going to reorganize this into ln t over 1 over t. Using L'Hospital's rule, this is going to become 1 over t over negative 1 over t squared, which is the same thing as just negative t, which as we go to 0, just goes to 0 as well. So overall, our answer is just going to be x ln x minus x. That's the straightforward way to do it that you guys probably all learned in school, but we're going to go ahead and look at some other very cool methods. So the next method, which is actually the next easiest method, is actually Feynman integration. So we're definitely jumping up in difficulty. And the reason that Feynman integration is good for integrating the natural log of t is because the derivative with respect to one variable, I guess I should use the partial derivative of x to the a with respect to a is just x to the a times ln x. In general, the derivative of something to a power of a variable is just that same thing times the natural log of the base. So we can abuse this because we know that the integral from 0 to x of t to the a dt is just going to be equal to x to the a plus 1 over a plus 1. Now all we have to do is differentiate both sides with respect to a. So technically not Feynman integration, it's just differentiating under the integral sign. So we get that the integral from 0 to x of t to the a ln t dt is equal to, now let's just go ahead and use the product rule, so negative x to the a plus 1 over a plus 1 squared plus x to the a plus 1 ln x over a plus 1. And then we just go ahead and set a to 0, and that makes this just disappear. And we're just going to get negative x over 1. So just negative x right here. And this is just going to become x ln x over 1. So overall, our answer is just x ln x minus x. All right, now they're going to jump up pretty significantly in difficulty, because we're going to have now a bit of a functional equation here. So let's go ahead and jump into that. So I'm going to let f of x equal the integral from 0 to x of x ln x, or of ln t dt. Now something really useful about the natural log is that when you go ahead and substitute in a natural log, when you have natural log of something times something else, you can split those apart really easily. So this allows us to let t equal x times u, and that way dt is going to be x times du. So we're going to get the integral from 0 to 1 of x times ln xu du, which is the same as the integral from 0 to 1 of x ln x plus x ln u all du. And overall, this is just going to be x ln x plus x times the integral from 0 to 1 of ln u du. And I'm just going to go ahead and take this ln u du, and I'm going to let this equal some arbitrary constant b. So we know that the integral from 0 to x of f of x, or of ln t dt, is x ln x plus bx. However, also, if we differentiate f of x, we get that f prime of x equals ln x. So this has to remain true on the other side. So let's go ahead and differentiate, and we can pretty easily just solve for b. So when we differentiate, we're going to get that f prime of x equals ln x equals ln x plus 1 plus b. So this means that b is equal to -1. And f of x equals integral from 0 to x of ln t dt is just equal to x ln x minus x. All right, let's go ahead and work on our next method, which is going to be using the definition of the natural logarithm. So the great thing about the natural logarithm is the natural logarithm, first off, is defined by the integral from 1 to x of ln t dt. Or, sorry, not ln t, that's silly. This is one of the definitions. There are a few different ways to define it, but this is the most commonly accepted one, and of course we know that it's going to work. So one way that we can actually do this is one thing that is really, really easy, unlike this definition, is integrating power functions. So 1 over t is a power function, and it just happens to be the only power function that is not so easy to integrate. So what if we instead let it sort of become a power function? So I'm going to go ahead and replace this with integral from 1 to x of the limit as h goes to 0 of t to the h minus 1. Now notice that as h goes to 0, this is going to become t to the -1, which is exactly what we're looking for. And this is a really easy way to figure out a nice little approximation or way to represent ln x without using integrals or anything like that, because this is really easy to integrate. We can just interchange the integral and the limit here, and we're going to get the integral from 1 to x of t to the h minus 1 dt, which is just equal to the limit as h goes to 0 of x to the h minus 1 all over h. And this is a really cool definition of the natural logarithm. Now let's go ahead and apply this definition into our original integral that we're trying to solve. So we're going to have the integral from 0 to x of the limit as h goes to 0 of t to the h minus 1 over h dt. We're going to interchange the limit and the integral again, so we're going to get the limit as h goes to 0 of the integral from 0 to x of t to the h minus 1 over h dt. Now, when we go ahead and integrate this, we're going to get the limit as h goes to 0 of, now when we integrate t to the h, we're going to get x to the h plus 1 over h times h plus 1. And then at 0, it's just going to go to 0, and this is just going to be subtracting minus x over h. Now this looks really nice to deal with because we have this over h on both sides, but this over h plus 1 is a little bit annoying to deal with. So in order to simplify this, we're just going to do partial fractions. 1 over h times h plus 1. It's really easy to see that this is just equal to 1 over h minus 1 over h plus 1. And sorry that my h kind of looks like an n. I know my handwriting is a little bit of a problem. So once we have this, we're going to get the limit as h goes to 0 of x to the h plus 1 minus x all over h minus x to the h plus 1 over h plus 1. Now both of these limits are super easy to evaluate. This one right here, as h goes to 0, we just end up getting subtracting x. So, and this one right here, if we just factor out an x, we're going to get just the limit as h goes to 0 of x to the h minus 1, which is the definition of ln x. So overall, we're going to get x ln x minus x. All right, so that one was pretty interesting. That was method number 4, I believe. Yes, method number 4. And now we're going to go ahead and jump into method number 5, which I think is a really interesting one. Now for this method, we're specifically going to be looking at values. So we have integral from 0 to x of ln t dt, right? We're going to specifically be looking at values of x greater than or equal to 1. However, this same method can be applied to values of x less than or equal to 1. It's just easier to deal with values of x, and values of x greater than or equal to 1. So let's go ahead and visualize the area that we're looking at here. So if we go ahead and draw a graph, and let's draw the graph of ln x. Now, of course, we're choosing a value of x greater than or equal to 1, so let's just choose x to be right here. So this is x, and let's let this be ln x, because of course it lies on the curve, right? Now let's talk about the interpretation of this area. So we have two areas that are being considered in this specific integral. The first area is this one, which is the integral from 1 to x of ln t dt. And the second area is this area, which is the integral from 0 to 1 of ln t dt. But notice that since it's under the curve, it's counted as negative area, so we're going to have to subtract that area out. Now, let's look at a very similar graph. What I'm going to do is I'm going to reflect this graph about the line y equals x, which some of you may know is equivalent to taking the inverse function. So now we're looking at the graph of e to the x. Let's go ahead and label the same areas. So in this case, this ln x is going to be rotated, and it's going to be right here. So we're going to have ln x, and this is going to be x. And we still have this area shaded in, but remember this area is going to be negative, and we also have this area right here. And this area is actually a little bit easier to calculate, because in this case we only have to integrate e to the x, rather than integrating ln x. So let's go ahead and set up an expression for these two. So first we're going to subtract this area right here. So we're subtracting the integral from negative infinity to 0 of e to the x dx, right? That's what that area is. And this area here, we're starting up at x, and we're one way you could view it is just taking this big box right here and subtracting out the area right here. So that's just going to be adding the integral of from 0 to ln x of x minus the value of the function, which is e to the t dt. Now this first integral is super easy to evaluate, and we're just going to end up getting -1. And this other integral is also pretty easy to evaluate. We're going to get x ln x, and for this other one, we're going to have e to the t evaluated at ln x and at 0. So we're going to have -1 plus x ln x minus x plus 1. So those ones are going to cancel, and our answer is just going to be x ln x minus x, as we expected. And that was method number 5. So let's go ahead and jump into method number 6. Now we're finally going to use power series. So for this method, we're also talking about a limited domain. We're integrating from 0 to x, ln t dt. And we're only applying this to values of x between 0 and 2. And again, we can once we get our answer from this question, we can sort of just assume the analytic continuation will still apply to this integral. So really it'll work for values outside of 0 and 2, but we just don't want to make too many assumptions right now. So basically we just want to use the power series for ln 1 plus x, but right now we have ln t, so let's go ahead and fix that. We're just going to shift over our integrand. We're going to integrate from -1 to x minus 1. We're going to integrate ln t plus 1. Just shift it over the integral a little bit. Now let's apply our power series. So we're going to get the sum from n equals 0 to infinity of -1 to the n over n plus 1 times the integral from -1 to x minus 1 of x to the n plus 1 dx. Or, sorry, t to the n plus 1 dt. Sorry about that. And now we can just integrate that. So we're going to get the sum from n equals 0 to infinity of -1 to the n, t to the n plus 2 over n plus 1 times n plus 2 minus -1 to the n, -1 to the n plus 2 over n plus 1 times n plus 2. And notice that this -1 to the n cancels with this -1 to the n, and this is just 1, right? so we don't need to worry about that, and we can just replace this with a 1. So now let's split this into 3 different infinite sums. So first we have this infinite sum right here, which is going to be a telescoping series, and we also are going to need to split this up. So let's do our partial fractions real quick. 1 over n plus 1 times n plus 2 is just going to be equal to 1 over n plus 1 minus 1 over n plus 2, and you can go ahead and check that for yourself. So this telescoping series is going to be relatively easy to evaluate, and overall we're just going to end up getting the answer 1 for that total series. So this is now outside the summation, we're just subtracting 1, right? Alright. Next, let's go ahead and, why do I have a t? This shouldn't be t, this should be x minus 1. Right here, x minus 1, alright. So once we go ahead and split this up, we're going to get negative 1 plus the sum from n equals 0 to infinity of negative 1 to the n, x minus 1 to the n plus 2 over n plus 1. Then we're going to be subtracting negative 1 to the n, x minus 1 to the n plus 2 over n plus 2. Alright, so for this first summation right here, all we have to do is factor out an x minus 1, and we're going to end up with a very simple summation, which is the sum of negative 1 to the n, x minus 1 to the n plus 1 over n plus 1. And we can just recognize that this is going to be natural log of x minus 1 plus 1, which is just natural log of x. Alright, so we have natural log of x right here. And for this next part, we're going to have to do a little bit more simplification. Sum from n equals 0 to infinity of negative 1 to the n, x minus 1 to the n plus 2 over n plus 2. So one thing I want to do here is I want to go ahead and make this a plus sign and switch this to the n plus 1. Next, I'm going to shift over the index by 1, so I'm going to start n at 1, and I'm going to subtract everywhere I see n. So I'm just shifting over all the values by 1, so we're just going to end up with the sum. And this is just the series for natural log of x, as we saw before in our last series. However, we are missing that first term, the n equals 0 term, so we have to make sure to subtract that out. So we're going to get negative 1 plus x minus 1 ln x plus ln x. And the only thing we need to remember is we need to subtract out that n equals 0 term, which should just be, let's see, when we plug in n equals 0 everywhere, we're going to get x minus 1. And so once we go ahead and multiply everything out, we're going to get negative 1 plus x ln x minus ln x plus ln x minus x plus 1. And everything is going to end up canceling perfectly. We're going to get our expected answer, which was x ln x minus x. One more time. All right, that was a pretty good one. Now let's go ahead and move on to our last and final method. This was method number 6. Now let's go ahead and move on to method number 7. Now this one I put last because every time I've attempted it so far, I've made a mistake, so please bear with me here. There may be a few slight mistakes. For this one, we're going to be only applying to the case where x is greater than 1. We can do other cases. It's a little bit too difficult to make reason everything out when x is less than 1. So I'm only going to be dealing with the case of x is greater than 1, but believe me, other cases can be made. So in this case, we're going to use the definition of natural log again. So the integral from 0 to x of ln t dt is equal to the integral from 0 to x of the integral from 1 to t of 1 over u du dt. And now, in case you guys hadn't already guessed, we're going to go ahead and do some interchanging of the integrand. So let's go ahead and see what that's going to look like. First off, let's draw out a plot, and let's let this be u and this be t. Now the first thing we see, or actually let's put t on the bottom here. It might be a little bit easier to see. T on the bottom, u on top. First, we see that t goes from 0 to x. So we can just draw a line right here, and this is the line t equals x. Next, we see that u goes from 1 to t. So let's draw the line u equals t right here. We're going to see that u only goes from 1 to t. So let's draw the line u equals 1, which is going to be like right here, I guess. U equals 1. U is going to only be above this line. However, you see that since t goes all the way from 0 to x, let's first talk about where t is greater than 1. So where t is greater than 1, we just have this area right here filled in. And that's because t is going between u equals 1 and u equals t, while t is going between t equals 1 and t equals x. So that's how that lines up. However, in this other area right here, it's actually a little bit interesting because u is going from u equals 1 to u equals t. So u is actually going backwards or downwards. And so because of that, because it's sort of moving backwards, it's the equivalent of, instead of integrating from a to b, f of x dx, we're actually integrating from b to a. So we need to throw in a negative sign there when we're talking about that region. So first let's define this region. So we need to put a negative sign in front because that area is really a negative area, as I said, because we're moving backwards from u equals 1 down through that area. So we're subtracting, and now remember we're exchanging the order of integration, so we're going to define on the outside u. So u in this case is going all the way from 0 up to 1. So negative integral from 0 to 1 of the integral, and in this case t is going from 0 up to the line t equals u. So from 0 to u, and we're just going to have 1 over u, and then this is going to be dt du. And for our other integral, this is going to be a little bit more straightforward. Again, we're defining only u first of all. We can see that u goes up from u equals 1 all the way up to u equals x, which is this line right here. So u is going to go from 1 to x, and t is going to go from the value of u rightward until it hits that line t equals x. So it's going to go from u to x, and again we're going to have 1 over u dt du. So let's go ahead and do these integrals. This one on the left right here is really simple. It's negative the integral from 0 to 1 of 1 du, so it's just going to be negative 1. This other one on the right is a little bit more difficult. We're going to have the integral from 1 to x of x over u minus 1 du. So when we go ahead and integrate that, negative x plus, remember that the integral from 1 to x of 1 over u du is just going to be, the integral from 1 to x of 1 over u du is just going to be ln x. So this first part is going to be x ln x, and this next part is going to be minus x minus 1, just because we're integrating 1 du. And of course, we can cancel this with that, and our overall answer is going to be x ln x minus x. Bet you guys couldn't have guessed that by now, right? So that is the last method that I will be presenting in this video. This is method number 7. However, there is one method that I haven't included here, and the reason I did that is because you have to use the other methods in order to complete it, but I think it's a good homework problem for anyone who wants to try it out, and that is using a contour integral. So if you want to try and use a contour integral to show that the integral from 0 to x of ln t dt is x ln x minus x, I absolutely suggest that. If you want a hint on the contour, I'll give you one right here. Contour is going to look something like this, going this direction, and it doesn't have to be this size of wedge. It could also look something like this, right? It could be pretty much any size of wedge. And as I said, you have to either use Feynman integration or you have to use integration by parts. However, it's still a really cool method in order to show this integral, and it's a really good practice in complex analysis for any of you who want to try that. So yeah, I hope you guys enjoyed this video. I had a lot of fun making it. It was really an interesting, quite an interesting set of integrals that we did here. Set of integrals, I guess it was all the same integral over and over again, but I just love being able to show that there's a million different ways to approach any problem. In this case, it's really 7 or 8, but you don't really have to know one specific method. You can always figure out another way to solve it. So yeah, hope you guys enjoyed the video and all these methods to solve this one integral, and yeah, I'll see you next time.